Okay, so what I will do today is I will prove that the eigenfunctions uh, of the Laplacians are in fact optimal for representing a very specific set of functions, family of functions. These functions would be the set of functions with bounded Dirichlet energy, such that the squared uh, norm of the gradient is bounded. When I'm saying the square, when I'm defining the Dirichlet energy, it is officially defined like that. It's the integration over gradient of phi of sorry. Let's do it explicitly. D over dt of phi of t, and I square it. Okay, and I would like the integration to be bounded. For this, if this is the only knowledge I have about my functions, then my claim is that taking the eigenfunctions of the Laplacian operator, okay, this would be my Laplacian operator with a minus sign. So this would be my eigenfunction. These would be the optimal basis. Sorry, the optimal basis for representing function. Let me do it formally. So what we will provide is that the best representation basis in terms of truncated representation. Let me share what is truncated representation. For a specific family of signals, this is all the signals with bounded Dirichlet energy are given by a specific family. Okay, so in general, this family would be called beta I of t. And if I have an infinite number of functions, then I will need an infinite number of the basis would have an infinite dimension. When I'm referring to a truncated error, then what I'm doing is I'm taking my function, which I would like to represent, projecting it into my members of my family, of my basis, of my set of functions, and then multiplying each and every function with this scalar coefficient, okay? And when I'm saying truncated, I'm referring to the fact that rather than scanning, projecting through all infinite dimensional, infinite number of betas, I'm restricting my projection to have only k members, okay? And so thus this is the sum. So I'm subtracting from my function the projection onto the k first members of my family beta, okay? And what we would like to do is find the basis that would minimize the following measure. It should choose the worst possible element for my family, such that the beta would minimize the representation error. Okay, and it should obviously apply to any k larger than 1. I mean, I can truncate my basis after 1, after 2, after 3, whatever. We'll call the family of such functions that are captured by that. We denote this family as phi of omega. And this is the problem that we would like to deal with in this lecture. Let's see what is going on. So again, now we narrow rather than any set of functions. I would like my family of functions to be those for which the Dirichlet energy is bounded. Okay, this is the set of the functions. And without loss of generality, I would also like to assume that everything vanishes along the boundary. So if this would be my boundary between 0 and 1, I would just deal with all the functions for which I have 0 values at the boundaries. Okay, so this would be my phi of t that belong to this family. And the other thing that I know is that if I integrate over the square derivative of this function, then it is bounded. This is a really strong assumption, but it is still a general assumption. What we will show is that if I ordered my eigenfunctions of the second order derivative, okay, if I order them from the smallest to the largest, so here I have the eigenfunctions, and this would be equal to the eigenvector. So this would be, sorry, the eigenvalues. And if I somehow order my eigenvalues so that they are ordered from the smallest to the largest, so this would be the other way around. Okay. So they are ordered in an increasing order. So this would be 1, this would be 2, etc., etc. So if lambda I is always smaller or equal to lambda I plus 1, then, and the corresponding eigenfunctions are transmitted one at a time, then this would be the optimal basis in the sense of the error that I've shown in the previous slide. Let's do it. So first of all, a note about Dirichlet energy. If I'm looking for the second norm of the gradient, then this would be the gradient inner producted with itself. Written explicitly, this would be the multiplication of the first derivative of phi with the first derivative of psi. And by integration by parts, I can get rid of the scalar part. I mean, of the first part, and then what I get is nothing but the second. I mean, this would be equal to 0 because of the boundary conditions. And what I get is nothing but the inner product between phi and the Laplacian with a minus sign that multiplies the function itself, that operates on the function itself. And again, we could solve for this. I mean, we could produce the eigenfunctions, eigendecomposition of this operator, which would be nothing but the harmonics. And it is easy to see that this would be the harmonics because as we take a second derivative of an harmonic function, we obtain the same harmonic function up to some scalar, and this would be exactly the scalar, complex scalar. Okay. What else do we know? We assume that EIs, okay, EIs of T are, by the way, it applies to any dimension. So are the orthonormal basis for L2. It's an infinite orthonormal basis. And this is how you get it. I mean, it's an eigendecomposition of the Laplacian, exactly what I've shown in the previous slide. And I also assume that my eigenvalues are ordered from the smallest to the largest. Okay. So when I increase my number of members of the family, the eigenvalue would also increase. Okay, now warm up, an important property. If I'm looking at the Dirichlet energy, okay, this is the Dirichlet energy. By definition, this is what is written here. It's the inner product of the gradient with itself. It would be nothing but, as we have seen 2 slides ago, the function with the operator, with the Laplacian operator on the function. Writing everything explicitly, what we have is, first of all, we represent the function in the E basis, and then the Laplacian on the function in the E basis. This is just an expression of each of these functions in the natural basis. Okay. Now what we can do is use the fact that the eigenfunction or our functions are orthonormal to one another. So at the end, what would survive is just the multiplications of EI with EI. Okay. So what I have is the inner product between phi and EI, and the Laplacian minus the Laplacian and EI. Okay, let's play with it a little bit further. What I can do with this part is, again, apply integration by parts in order to move the Laplacian from phi to the eigenfunctions, which is what we have done here. Now we have the composition of the. I mean, we already shown that we have this decomposition that Laplacian of E of I is equal to nothing but lambda I E of I. So we use this fact in order to move from this equation to that equation. And what we and note that here what we have is nothing but a scalar, so we can pull it out of the equations, and then what we have is that the Dirichlet energy is equal to nothing but psi EI, okay, squared. The norm of the coefficients, okay? So this would be equivalent to the Dirichlet energy. So let's call it as result number 1. This would be result number 1. Okay, and this was our definition of functions and eigendecomposition of the Laplacian. Let's move on. We have the following theorem. If we use, in order to represent phi with only k members of the eigendecomposition eigenfunctions of the Laplacian, then what we have is the following theorem. It says that the residual is always, that the error would be smaller than the energy of the Dirichlet energy divided by the next eigenvalue. Okay, and it makes sense now to order. Okay, so this would be result number one. We call it theorem one, as we said here. Let us prove this theorem. So this is our representation error. We subtract from phi the projection of phi onto the EI, which means that if phi is equal in the infinite basis to the sum of I equals 1 to infinity, and we subtract this part, then what we get is nothing but the residual of the sum, okay? So it would be projecting my phi onto the rest of the basis, of the natural basis, and this would be the value. And we have already shown, and now what we are doing is we are using the orthogonality of EI to show that if I'm inner producting this one with itself, what I would get is nothing but sum over the coefficients of projecting phi onto the E basis, but the sum should be along the residual, the subspace at which I'm not using the eigenfunctions of. Okay, so this would be the first part of the proof. The second part of the proof is basically using the result that we have seen before. This is this result, this equality. Okay, so we can write the Dirichlet energy as the following sum. Okay, now let us move and truncate this sum and remember all of those are positive numbers. So now I would take only part of the sequence. Okay, so I truncate it and I negate. I'm basically eliminate the first k elements, so I get this inequality. And now, since the lambda i's are ordered from the smallest to the largest, I can take the smallest of this residual, which would be lambda k plus 1. Remember, lambda k plus 2 is larger than lambda k plus 1. So let us just assume that I'm taking the smallest of all of these elements. And this is why I can further enhance this inequality. Okay, so I have the inequality that this part is smaller than that part. Okay, and in total, what I basically have is that this part would be the error, okay, which is what we have seen over here, which is smaller than that part divided by lambda. Okay, which basically proved the following theorem. Okay, so this is one part. So I have some strange way of looking at my error if I would have represented it with the eigenfunctions of the Laplace-Beltrami operator. Now let's move to the second theorem. And the second theorem is telling us the following interesting fact. Assume that I'm now avoiding my natural basis. I'm selecting a different basis. Let's call it beta. It would be a completely different basis. And now this beta, and this beta can be any beta that I'd like to choose. Then what we'll show is that rather than having the following fact where I can bound my error, what I would claim is that if I project my function onto these betas, onto these k first betas, and this beta can be any function that I've chosen to use, but once I've chosen it, it is fixed, then this would always happen. I mean, my error would be larger. Unlike the previous one, it would be larger than the Dirichlet energy divided by the k plus 1 eigenvalue of the solution of the Laplacian operator. Okay, of the decomposition of the Laplacian operator. And if this would be correct, then indeed I would have finished the claim that my E I family of functions is optimal. For that, we do something which is called Poincare trick. I will refer to you to the relevant paper in order if you don't feel comfortable with that. And what we'll do is we'll select a function phi which has k plus one. Which belongs to the ek plus one subspace of the natural basis. So if I'm now examining what would happen until the kth element, I would like to choose my function so that it would be k plus one. It would have k plus one coefficients in the natural basis. Okay. Now I can select. I have the luxury of selecting phi any way I want, and specifically, I would choose one which would have zero support on the first k beta, on my family. So it has a k plus one elements in the natural basis, but zero elements in the k subspace of my betas. I can do that because I have k equation with k plus one unknown, so there is a non-trivial solution. Okay, so this is the way I would represent my phi function. Again, it has existence in the k plus one natural basis functions, but all the coefficients would be equal to zero if I project it onto the beta. Now let's see what is going on here. What's going on here is, in fact, the residual. I mean, if I would look into the residual of projecting beta projecting phi onto my beta would be nothing but the energy of the function itself, okay? Which would be nothing but summing all of these coefficients if I would have projected it onto the EI basis, okay? So this would be the energy of the error. On the other hand, recall that the energy of the Dirichlet energy of the signal we have shown that this is equal to this part, okay? And it would be nothing but, let's see, it would be nothing but lambda. Remember that I can, okay, so it would be nothing but sum equals I to k plus one, because this is where my functions live. Lambda times the ci squares. Well, remember, the ci's were nothing but phi projected onto the ei element, okay? These will be my ci's, okay? Now, what I can do is I can choose the largest eigenvalues of all, okay? Which would be nothing but lambda k plus one. And this is where I get this and pull it out of the summation. And this is why I get this inequality here, which is nothing but, remember what this part is. This is all this would be basically the error of projecting phi onto the BI elements, okay? Remember, this was equal to the energy of my signal, okay? This was equivalent to the energy of my signal, which was nothing but the following error, the definition of the error, okay? So now what I need to do is divide both sides by lambda k plus one, and indeed, with this inequality, get the second part. So let me sum up what we had until now. The theorem one showed us that if I choose the natural basis, what I would get is the following Weyl inequality. If I get any other basis, I can choose my function phi so that I get the error always larger than this bound. Okay, so this is why EI is optimal basis for the family of functions with bounded Dirichlet energy. Now, at home, what I would like you to do is repeat the whole stuff for the uniqueness. And in the uniqueness, you apply exactly the same trick, this trick of defining your function to be to exist in the k plus one E dimensional space. And in order to make the homework simple, you should assume a simple basis, so that a simple spectrum, so that lambda 1 is always smaller than lambda 2, etc., etc. You don't have multiplicities of eigen values. Okay. References. This is the important references. This is the important reference. And if you'd like, you're also welcome to look into this one where there is a much more complicated proof that applies for digital signals rather than continuous ones. Thank you. Let me try to now stop.